Alrighty then, corn children. This is a little review of sigma or summation notation. The question is, what on earth are we supposed to do with this? It looks like Greek to me. That's because it is a Greek letter sigma, and we need to make sense of this. Some of you struggle, so let's go at it. First of all, when we see a sigma, this automatically means that we will be adding up, that's right, adding up terms that follow a pattern. What pattern, you ask? Well, if we know sigma notation, the pattern sits right here. It's just this simple. We start by looking at the counter numbers, the index numbers, one could say. At the bottom, there's a 0. At the top, there's a 4. Here's what this means. Starting with the number 0, and yes, these are always integers, always. Starting with the number 0, we will fill 0 into the index number I. So my first term will be 0.5 times 0 plus 2, filling in the 0. It is a sum. It is a sigma notation, so it is automatically added to. The next term would be add 1 to the counter. It's always a whole number, integer. It's always an integer, and we always add 1. So the next number is 1. I fill in a 1. And then I fill in a 2. And then I fill in a 3. And then I fill in a 4. And you can hear from the finality in my voice that I'm done. How do I know I'm done? It's the final counter number. From here, we math. This is going to equal 0 times 0.5 is 0 plus 2 is 2. The next term you do the math is 2.5. The next term, do the math, 3, then 3.5, and finally the number 4. Well, isn't that clever? Take a look at this. The sigma notation has given us a sequence of numbers that are actually going up by 0.5. Well, you said they're always integers. Not these numbers, people. These numbers are always integers. These numbers always go up by 1. But depending on the notation here, the pattern, that will determine how the final result is. Please notice with me that these numbers are going up every single time by 0.5. That sounds familiar. Sure enough, in our notation, the 0.5 is right here multiplied by the I, the counter number. Because we started with 0, it's not random. Because we started by 0, as it turns out, this first number is the value right here. It's almost as though, yes it is, this is of the form mx plus b. And when it's mx plus b, these numbers will go up by the m, and if you start with 0, this is automatically the b. And you know what, campers? It goes the other way. If we start with these numbers, we can create a sigma notation using mx plus b form. No, that can't be true, Mrs. Klein. Yes, it can. Here's an example. I have here a sequence of numbers, and they are added together, and there's a pattern. 3 to 3.6. 3.6 to 4.2 to 4.8 to 5.4. It's almost as though these numbers are going up by 0.6. Now, if you want to take the time to check that, pause the video, and you can add 0.6 to each of these numbers, and sure enough, it's going up by 0.6. So here's what I can do. I can write this in sigma notation? No. Yes, I can. First of all, because the numbers are going up by 0.6, this will be of the form mx plus b, where the 0.6 is the m. Now, you can use any counter letter you want. Tradition says I for an index number, so I'm going to use 0.6 times I. Simple enough. If you start with 0, can I recommend you start with 0? If I fill 0 into this, I will need this expression, 0.6 times 0 plus something, the first counter number, to equal the first number in the sequence. What could that number be? B, get it? 3 for B. If you start with 0, this is the B value. I would fill in 0 and I would get 3. I would fill in 1 to get this. Fill in 2 to get that. Fill in 3 to get this. Fill in 4 to get that. Fill in 5 and we get the last one. Look at that. That's just exciting, isn't it? But wait, don't order yet. There's more. What? What do you mean there's more? Well, let's play pretend. Can we? I mean, this problem is done. That's the sigma notation. But let's play pretend. Yeah? I'll be a duck. Pretend it wasn't just these numbers. What if these numbers were being filled into a function? What if each of these numbers was the input to a function? How do we do this now? What do we do? It's just this simple. F of this, F of this, F of this, F of this. We make this F of. No, that's crazed. Crazed, I tell you. Wait, let's pretend again. What if we actually know the function? What if we know that f of x is some kooky, crazy function, like 3x squared minus 7? Well, what does this mean? This means, in my expression, everywhere I see an x, I'm going to replace it with 0.6 I plus 3. No! Yes! All right, so here's the sigma. I is 0 to 5. Now, we're going to go to the F notation. I will take the x out. So it is 3x squared minus 7. I put this into the x location. Now we have a sigma notation that will mirror, mimic, find the answer to this expression if that's our function. Man, I wonder if that ever comes in handy. This is the process for doing our Riemann sums, isn't it? Did you think to yourself, gosh, that reminds me of Riemann sums? Yes, this is the inner part of the Riemann sum. Perhaps these are the values for the left Riemann sum, the heights of those rectangles. Perhaps these are the values for the right Riemann sum. These could be those heights for those rectangles. That's how we do it. Now, of course, you still have to type this in. Now, keep in mind, if you're using the TIs, when you use your sigma button, these two parentheses automatically show up with the sigma feature. So real quickly here, we're almost to a 10-minute video. Real quickly, we can go into the Alpha F2 shortcut key, find number 2, and then you literally type what you see. You can use X, you can use I, you can use any variable, but it will work. All right, corn children, there it is.